Alright, let's see. So we've covered displacement and velocity. Now it's time to move on to acceleration. This is the second topic of our three. Acceleration. So up until now we've looked at objects that are traveling at a constant velocity. This makes it much easier to solve problems for their position and the time it takes for them to travel. However, not all objects travel at constant velocity. What about objects whose velocity is increasing or decreasing at a constant rate as they move? This change in velocity, delta v, over time, is known as acceleration, which we express as a. A means acceleration. Acceleration has both a magnitude and direction, and its direction depends on the sign of delta v. So for instance, if the velocity is increasing, say we have this car and it's accelerating, getting faster and faster, its delta v will be greater than 0. That's a positive delta v because it's speeding up. That means that its acceleration is also positive. So positive acceleration, speeding up. Say this car is coming into the driveway. They see the house up ahead, so they're going to slow down. Now they're going fast and then slowing down. That's going to be a delta v that is less than 0. That's negative. That means its acceleration will be negative. So again, acceleration has both magnitude and direction. Its direction is the sign it has. So like velocity, acceleration can be represented on a graph. However, when we go to graph acceleration, instead of graphing position versus time, we're going to get rid of position, we'll be graphing velocity versus time. This makes it easy to find acceleration on a graph. So once again, we're going to use the slope of a graph to find the object's acceleration. So let's say there's an object. It's traveling for 6 seconds. There's 6 seconds. And in 6 seconds, its velocity increases from 0 meters per second, 3 meters per second. So now we have this line, 3, 6. Alright, so now we're looking for rise over run once again, so we can find the slope of the graph. So this rise, the delta v of t, is going to be 3 meters per second, and the run, delta t, is going to be 6 seconds. If we divide again to find slope, we get 3 meters per second over 6 seconds. That simplifies to 0.5 meters per second squared. That's the acceleration. It's also the slope of the graph. So at this point we have this equation for acceleration. A equals delta v over t, or the change in velocity up here, divided by the time during which that change occurs. So this equation is going to come in handy when we're deriving some other equations that have to do with the movement of objects with constant acceleration. So let's start by rewriting this a little bit. We'll keep the a over here. We have a equals, delta v will express as the final velocity minus the initial velocity, because that's a change, divided by t. So let's see what we can do here to simplify. We're going to multiply the t over to this side. You get at equals v final minus v initial. Then let's add v0 to both sides. We end up with that the final velocity equals the initial velocity plus acceleration times the time during which the motion occurs. This equation will allow us to find the velocity of an object that's moving with constant acceleration. So let's take an example. Say we have a person running. It's a girl, and she's running. She starts from rest, and after 3 seconds, she's been accelerating at a rate of 1/3 meters per second squared. That's a. And of course, the 3 seconds is time. Let's plug this into the equation and see how it works. So her final velocity is going to be equal to her initial velocity, which is 0 because she was at rest, plus acceleration 1/3 times time, 3. We can see now that her final velocity is going to be 1 meter per second. So that's the equation we're going to use when we're finding velocity from situations with constant acceleration. So now we're going to move on to an equation that will help us find displacement in situations with constant acceleration. So we're going to start with this equation I have up on the screen here. So delta x, that's displacement, that's what we're trying to solve for, equals 1/2 times v initial plus v final. So that quantity right there is the average velocity of the object as it accelerates. We know this because an average is going to be 1/2 times the first velocity plus the second velocity. And we know that it's constantly accelerating. So displacement equals average velocity times time. Alright, so from that equation, we're going to substitute the equation that we just derived on the previous slide, which is v final equals v initial plus at. So as you can see, there's a v final up here and a v final down here, so that's going to make it easy to substitute. So let's rewrite this as delta x equals 1/2 times v initial plus at, and then remember to multiply by that t that's still over there. So now we can combine like terms to get delta x equals 1/2 times 2v initial plus at times t. So now we're going to distribute the 1/2 into this expression right here. That'll come out to delta x equals v initial plus 1/2 at, and then remember to carry down this t that we're still multiplying. So finally, let's distribute the t. Now we're left with delta x equals v initial times t plus 1/2 at squared. Alright, so this equation is going to be very useful when we're looking for displacement, the delta x, and we know something about the initial velocity, maybe the acceleration, and we know the time during which this motion takes place. So that'll be the equation we'll use for displacement. And another thing to keep in mind is that if we're really looking for displacement, this delta x, this is going to be x final minus x initial. And so that'll equal v0t plus 1/2 at squared. And if we're looking for this final position, which is really what we're looking for in situations of displacement, we're going to have to add the x initial back to both sides. So this equation is usually officially written as delta x equals x initial plus v initial t plus 1/2 at squared. That's for displacement. So now that we have equations relating displacement and velocity with time for situations with constant acceleration, we're going to derive one last equation, which will be helpful in problems where you know the position, the velocity, and the acceleration of an object, but not the time during which the acceleration occurs. So as you can see, we're starting with the same equation for the last slide. This displacement equals average velocity times time. But we're going to do something slightly different to derive this next equation. So first of all, we're going to multiply both sides by 2 to get rid of this 1/2. So we have 2x equals t times vf plus v0. Now we're also going to divide both sides by the quantity vf plus v0 to isolate t. So now we get that t equals 2x over the quantity vf plus v0. So we're going to take this quantity we got for t. We're going to plug it into the equation, which might look familiar from before. V final equals v0 plus at. So as you can see, this t is going to fit nicely into this t over here. So now we get vf equals v0 plus a times 2x over v final plus v0. So we're going to start by subtracting v0 from both sides. Now we have vf minus v0 equals 2ax over vf plus v0. We're also going to multiply this over to the other side. So now we have the quantity vf minus v0 times vf plus v0 equals 2ax. So you might see here, this is sort of similar to the formula you learned in algebra with the difference of squares. So as you can see, if you FOIL this equation, multiply, distribute everything, you're left with vf quantity squared minus v0 squared equals 2ax. Sorry, you're following me up here to this other line of text. Alright, there's only one last step. We're going to add v0 squared to both sides to get our final equation, which will be v final squared equals v initial squared plus 2ax. That's the equation. So as you can see, there's no time variable in this equation, which is going to make it useful in situations where you don't know how long the acceleration is occurring for, but you know all the other variables in the equation. So we'll see this coming up in a few practice problems. So I'm going to do a brief summary of the acceleration equations we've learned so far. First, we have this equation that measures displacement when we know time and acceleration and velocity when we're trying to find how far the object has traveled. Next, we have an equation for velocity. This is the final velocity of an object that's been accelerating at a rate of a. This is good for when you know the time, you know the acceleration, you know maybe there's an initial velocity or maybe it started at rest, and you're just trying to find the final velocity. And then finally, we have this one I just went over on the last slide. This is the equation where you don't know anything about time, but you do know things about acceleration and about the change in velocity, so from the initial velocity to the final velocity. So that's a summary of acceleration. Alright, so now it's time to do some acceleration practice problems. In this situation, a car accelerates from rest, so that's 0 meters per second, to a velocity of 6 meters per second in 2 seconds, so that's the time. We want to find how far the car travels, delta x, that's what we're looking for. So let's start by solving for acceleration. So we know that a equals delta v over t, which in this case is 6 meters per second over 2 seconds. We can simplify that to get 3 meters per second squared. Now we can use the equation we just learned for displacement, delta x. So delta x equals x initial plus v initial t plus 1/2 at squared. In this case, the initial position is 0 because it's not really specified. We just want to find how far the car travels. The initial velocity is also 0 because of rest. Time is 2 seconds, but again, the 0 is going to cancel that out. So the only term we're really left with is this, the 1/2 at squared. We've solved for a, that's 3 meters per second squared, and we know that time is 2. So we have all the variables we're going to need. So now we see delta x equals 1/2 times 3 times 2 squared. And we can simplify that to get delta x equals 1/2 times 12 equals 6 meters. So now we're on to a second practice problem for acceleration. So in this case, a driver is traveling at 21.8 meters per second, that's v initial, and he sees a cat 101 meters away. How long will it take for the driver to come to a complete stop 2 meters before the cat? So you want 2 meters of space there to save the cat. Alright, so what this really means is that the driver is traveling a total distance of 99 meters as he stops. So let's first solve for the car's acceleration. We don't know anything about time yet, so we're going to use this equation v final squared equals v initial squared plus 2ax. We know v final, that has to be 0. And we know v initial, that's 21.8 squared plus 2. We're solving for acceleration, and we know that the position is 99. So we'll square the 21.8. We get the v0 equals 475.24 plus 198a. We're going to subtract 475.24, bring it over to the other side. So now we get negative 475.24 equals 198a. And as you can see, we divide by 198, and then we get a equals negative 2.4 meters per second squared. So once we know the acceleration, we're going to use this equation that we got from before, v final equals v initial plus at. That will allow us to solve for the time that it takes the driver, t, to stop before hitting the cat. So once again, we have this final velocity 0 equals initial velocity 21.8 plus acceleration, we found that, negative 2.4 t. So now we're going to add 2.4 t to to both sides. We get 2.4t equals 21.8. Divide the whole thing by 2.4, and we get that t equals 9.1 seconds. That's the entire time it takes for the driver to stop.